Hello and welcome to this presentation. Well, I could call it an animated introduction to vibration analysis, but actually that's a webinar that I performed recently, and we received so many questions afterwards, I thought, well, let's create another video answering all those questions. So I am Jason Tranter, the founder and CEO of Mobius Institute, and you can still see the original presentation if you'd like to watch that. Anyway, let's go through some of the questions. What is the best way to be trained and certified? Okay, we asked that question ourselves, but hey, we are doing this kind of for a reason. So the answer to that question is, of course, Mobius Institute. We have training centers in over 50 countries. All of our courses, category 1, 2, 3 and 4, are taught in many languages. You can go to a training class. We train over 4,000 people that way each year, and then we have distance learning and we have e-learning. One of our great strengths, I guess, what we're uniquely known for is we create lots of animations and simulations, which you would have seen in the original webinar and you'll see more of today, and that just makes all this stuff so much easier to understand. Anyway, our certification follows the ISO standards and we are accredited. Our certification program is accredited, and since we started running these sorts of courses since 2005, just in these category 1 through 4 courses, we've trained over 26,000 people. That's just since 2005. Anyway, enough of that. Okay, so the first question is, what generally causes harmonics versus a single peak in a spectrum? So, if I have just a single pure source of vibration, just at one frequency, I just get one peak in the spectrum. Now, if you can imagine a machine rotating, if it was just smoothly operating, like just purely unbalanced, it would just have one frequency. But a lot of the vibration we actually experience, like the forces involved with the vibration, aren't purely sinusoidal. If you looked at it more closely, it's actually distorted a little bit. Now I'm going to show you that in just a moment. And that creates harmonics. So instead of just seeing the peak in the spectrum related to the frequency, you see peaks at twice that frequency, 3 times, 4 times, 5 times. So that's one way we can see those peaks. But the more distorted it becomes, the more harmonics we get and the higher the amplitude is of those harmonics. And if we get to the point where we're actually experiencing impacts, like for example, once per revolution, bang, 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 because of looseness, let's say, or within a bearing, each time the rolling element hits the damaged area in the outer race, we see an impact and we get harmonics as a result. So here is a pure, simple sine wave, and because it's just one frequency, and I just wind that down a little bit, because it's just one frequency, it's a beautiful sine wave. There's just one frequency as a result. But if I play with this signal and I actually distort it, and you can kind of see I'm changing the shape of it a little bit. I won't go into too much detail of what I'm doing to it, but you can see this is not a sine wave anymore, and lo and behold, we get harmonics. Okay, they're little harmonics, but they are harmonics. So, if there were stronger impacts, we would see actual harmonics that are much higher in amplitude. So, what I thought I'd show, okay, if it was a time waveform that looked like that, so not purely sinusoidal, we would see harmonics for sure. Now, I'm going to use a little simulator that is there to demonstrate what happens when bearings are damaged. Now just bear with me for a second. So what we're seeing over here, oops, better keep it on screen, we're not seeing it all on screen. Anyway, so there's the sine wave of just the shaft turning and the bearings are just fine. But if I have a little bit of damage on the outer race here, then each time the rolling element rolls over that area of damage, we get this little spike. Now, the way this simulator works, it's just actually trying to say, hey, if it's just a tiny little spike, you may not see anything in the spectrum. But what I'm going to do is I'm going to make the spike much worse, and you see these harmonics come up. And in fact, we can just isolate just the spikes, and that's what's causing, these peaks. Now, in this instance, the frequency we have here is they're not generating harmonics of 1x. So this is my 1x peak, this is my running speed peak, and there are questions on that coming up. So if you're not sure what I mean by 1x, you will in just a minute. So there would be 2x here and 3x and 4x, and because it's a rolling onward bearing, I'm actually seeing harmonics of 4.22. I happen to know that. So at 4.22 and 8.44 and 3 times that and 4 times that and 5 times that, we get peaks in the spectrum. Anyway, that's probably enough said about harmonics, but that's why. So anytime you see harmonics in the spectrum, you got to think, aha, what is happening inside the machine? Is it just sort of slight distortion, and there will be weak harmonics? Distortion because as the shaft rotates, maybe it's more stiff vertically than horizontally, so it gets a little bit of distortion, like it's not a pure sine wave. Anyway, if you see really strong harmonics, you've got to say to yourself, okay, what is impacting? Why does mechanical looseness generate multiple harmonics of 1x vibration? And really, I kind of just answered that question. Mechanical looseness involves impacting either within the bearing itself due to excessive clearance. That can be sort of within the clearance of the bearing, or in between the outer race and the housing, or even just the machine as it vibrates up and down. We might have impact. So there's rotating looseness, mechanical looseness. But anytime we have, for example, a once per revolution impact, we will see 1x harmonics. So we'll see peaks at 2x, 3x, 4x, and so on. So in this animation, hopefully you can see, as it rotates, we see this impacting going on, and that could happen also in the between the outer race and the housing. I mean, that's if it's loose. And of course, my animations are really exaggerated, and anyway, when there's looseness, we get that impacting. Now, I've mentioned the word 1x a few times, and this question is, can you elaborate a little more on 1x, 2x, etc., and running speed? What is that, and how does it correlate to being able to determine where on the machine the fault is located? So, number one, 1x simply means 1 times the running speed of the machine. So let's say we've got a motor and it's turning at a particular speed in CPM. You often quote it in RPM, but a lot of people work in Hertz as well. So it has a speed. Well, because a lot of fault conditions occur as the shaft rotates once per revolution. So for example, unbalanced, we get this force, and you'll see it in a moment, once per revolution. Rather than quoting what it is in CPM or Hertz, which is meaningless unless you happen to know the speed of the machine, it's easier just to say 1x, 1 times the running speed, 2x, 2 times the running speed. And for most vibration analysts, as soon as you say, oh, there's a big peak at 1x, their mind goes off in one direction. Oh, there's a, the vibration at 2x has increased. Their mind goes off in a different direction. 3x, 4x, 5x, same thing. We know what that means. We don't need to know what the speed of the machine is. But if someone said to us, oh, it's going up at 2,900 and something, you'd have to say, oh, well, I'm going to assume that I know what the running speed is, and, it takes an extra step. So that's the first part to the question. Second part is, okay, if we do have unbalance, the spectrum might just have a big peak at 1x. If, for example, there was misalignment, I could, and I'm going to explain this a little more in just a moment, I could see a peak at 2x and maybe one at 3x and even one at 4x, and it depends actually on the coupling. But looseness, that's what we mentioned just a moment ago, or I mentioned. There's my 1x peak, but I also see one at 2x, 3x, 4x, 5x, 6x, and so on, and they are the harmonics. And in this case, I also see the noise floor, that's the bottom of the spectrum, it lifts up often when we have a lot of impacting going on. It excites resonances in the machine, and the vibration, the general sort of noise, if you like, the general sort of background vibration also increases in amplitude. So, number one, in terms of the 1x vibration, we often see that because of unbalance, in some situations misalignment, if the shaft is bent, if there's eccentricity, and really anything where once per revolution we got some sort of force. So, normally, even with just a normal machine, we will see vibration at once per revolution at 1x. You'll never balance a machine so well that there is no vibration. It may not be obvious in some cases which peak is the 1x, and I've got a question about that coming up. But if, for example, we have a fan that you can see there, and because of unbalance, then once per revolution we've got this centrifugal force that makes it wobble, if I can use that term, as you can see there. It's actually wobbling sort of up and down. That impeller is actually turning in a circular motion, but it's actually rocking back and forward axially as well. So we would actually see vibration both axially, as in if we measured in this direction of the machine, but also radially, so vertically and horizontally. We would see 1x vibration. In this case, this isn't the best animation in the world, particularly with that great big key there, but if there's angular misalignment, then once per revolution, what I'm trying to show there is that the bolts are kind of being stretched at the top. Now this is obviously very exaggerated, but just to sort of make the point that once per revolution we've got this force in the axial direction, and we can see high 1x in that case. Now, we can have actual forces that generate the 2x and 3x vibration, but again we can also say, well, due to the misalignment, or for example cocked bearing and a bent shaft, we can see vibration at twice running speed. But there's always this debate about, well, is the machine doing something or creating a force twice per revolution or 3 times per revolution, or is it just that it's generating something at once per revolution, but because of the non-linearity, it's not a simple rotating force, it changes as it rotates, we see peaks at 2x and 3x. So in this case you can see a very bad case of offset or parallel misalignment, and we expect to see 2x vibration, for example, in this case, and perhaps some 3x and 4x. In this case, if the inner race was bent on the shaft, then each time it rotates, it generates a 1x vibration, but we often see peaks at the 2x and 3x as well. And of course, I need to say that we'll also see vibration at 2x and 3x and 4x for physical reasons. So we could have, for example, a machine with 2 lobes, or a coupling that has 3 jaws or 4 jaws, and that's going to generate vibration as well. So to kind of answer the question, I wasn't sure exactly what you wanted to learn with this question, but the fact is that with time waveform analysis, and especially phase analysis, it enables us to determine what the fault actually is. Because all of those things we just saw are physical motions within the machine. The bearing wobbling, the shaft wobbling, the fighting over the coupling, both offset and angular. It was all physical. And that makes the machine and the bearing housings respond in a certain way. So if we compare the motion vertically and horizontally, we can get a clear idea whether it's unbalanced or something else, and that can lead us to certain conclusions. We can see how the phase changes from one side of the coupling to the other side, and look, there's a lot of ways. It just gives us timing information, and that is the way to really properly solve why you're seeing vibration at 1x, 2x, 3x, and particularly those frequencies. Okay, so the next question is, I've ordered these in a certain order so they're all sort of relevant to each other. All these analyses depend on the assumption that we have the running speed estimated correctly. Yes, it really does. You really do need to know what the running speed of the machine is. because how do you know if it's unbalanced if you don't know what the running speed is, and therefore whether you're looking at the right peak and all those other things that I've said? Yes, you need to know, but if for some reason it's challenging to find out from the spectrum, because often the 1x peak is quite high and it's the dominant peak at the sort of the low frequency end of the spectrum. If you don't know, there are tools that let you measure it. There's a variety of tools, even a little stroboscope, and there are other ways. And then also, even with the spectrum itself, you can kind of reverse engineer it. Now, I'll make additional comments about that later, but when you're looking at a spectrum, you can say, well, if this peak was 1x, then I'd expect to see some other peaks at multiples if I've got fan blades or pump vanes or gear teeth or whatever. There's a certain way to kind of deduce which is the 1x peak. It's not perfect, but once you have an idea of what it is, it's then possible to make it accurate. Because, for example, if I knew I had 6 vanes, I can go to the 6x peak, figure out what the frequency is, and then divide that by 6 to get a much better estimate of running speed if I need it. Okay, so how can we ensure that we have the correct running speed estimated? So it was just another question, and as I just kind of mentioned, ideally we measure it and we know for sure, but if I knew there were 6 pump vanes or 31 gear teeth or something like that, I can look for those peaks and then say, well, okay, well, if that's gear mesh frequency at a peak that's 31 times running speed, I therefore know what the running speed is. There's a lot more I could say about that, but let's move on. Oh, here's a good question. What is the best conference to attend if you're interested in vibration analysis and condition monitoring and reliability improvement? Well, there is a conference called the International Machine Vibration Analysis and Condition Monitoring Conference. It's a mouthful, but it's a great conference, and we run those. You probably figured that out. We run them in the United States, in Australia, in Europe. So we've got one coming up in June in Antwerp, in Belgium. We just had the conference in Asia, which is Singapore, and in the future we're going to conduct them in Latin America, China. We're going to have mini events in England, and we're running a lot of these conferences. They really help people to learn. Anyway, I know you want another proper question, so I'll get on to it. What's your recommendation for routine vibration readings? Number one, you must measure a spectrum and the waveform. A lot of people measure spectra. Not enough people measure a waveform as well. This is a big topic, but the simple answer is you need to determine what the best settings are for the waveform, and I've got a couple of questions related to that, so I will elaborate a little bit. But it is important, if you possibly can, to measure the waveform while you're out there, because there are a lot of fault conditions where you can look at a spectrum and think, I believe that's the fault condition, but when you look at the spectrum, it'll either convince you that you were right or that you were wrong, and that you need to dig a bit deeper, or the waveform will tell you what's going on. But phase readings are really only for special tests, so you normally don't do that on routine tests unless you're an analyst and you look at the spectrum while you're out in the field and think, oh, there's 1x, 2x and 3x, or just 1x or just 2x or whatever, and you take a phase reading at that time. Now, I would personally suggest that you should get 2 spectra. One that gives you the vibration from about 0 to 15 times running speed, and that makes it crystal clear what's happening with all those 1x, 2x, 3x peaks that I mentioned, the 6x at the pump vane rate, for example, and other peaks in that area. Also when bearings fail, and we're talking sort of later stage failure here, but in the normal spectrum you'll see some peaks there. But a peak that's 0 to 100 times running speed, 150 times running speed, in units of acceleration actually, whereas this might be velocity, we see the higher frequency vibration from gear mesh and the rotor passing frequencies and these other frequencies, but we can also see humps in the spectrum from lubrication problems. We see other things as well, so it's kind of good. And the bonus is that with this spectrum that has a higher F max, we get, and particularly if the resolution's right, we get a really good time waveform that shows us just 4 to 10, just depending on your settings, 4 to 10 revolutions of the shaft, which is really good for time waveforms. We can really see what's happening as the shaft turns and the gears mesh or the rolling element bearings roll along. We can learn an awful lot. The spectrum with the lower Fmax, 15 times running speed, will have a longer time waveform, and you can see that's what this one's about. You see beats and random problems coming from the outside. You'll see cavitation. You'll see random problems in gearboxes, like as certain teeth come into mesh, then you only see the vibration at that instance. What I didn't mention, because actually the question didn't prompt me, but that's my fault, you should have a high frequency measurement as well, like enveloping, demodulation, peak view, shock pulse, HFD, these sorts of things. But there's some questions coming up on that soon, so I'll mention more about that as we go along. And so what would be the most important setting to use to have a nice time waveform? So I've mentioned that a little bit, but there are really two properties: the sample rate and the lines of resolution. The sample rate, it's kind of like if I was measuring a bullet smashing through glass or something like that. And I was trying to film it. So imagine trying to film something like that. You would want a lot of frames per second so that you could actually see the bullet flying through the air, hitting the pane of glass, and see all the glass shards fly off and all the rest of it. You've got a lot of frames per second, but then you might watch it in slow motion. If you use the normal sort of 50 or 40 frames per second, or 25 frames per second, I forget what it is normally, you would only have a few frames that caught any of that because it happened so quickly. Well, vibration analysis is just like that. The analyzer is inside digitizing the voltage signal that comes from your vibration sensor, like the accelerometer. And the sample rate, which is often controlled by the Fmax setting, determines how many conversions from that analog voltage signal to the digital waveform value, how many of those samples it takes per second, just like the frame rate in your camera. The higher the frame rate and the higher the sample rate, the more detail we see. So as the rolling element rolls over that damaged area in the load zone of the bearing, for example, we get to see that much more clearly if we've got a high sample rate, and that's why we need a high Fmax. So that's all fine, but that doesn't determine how many samples we collect. This setting, the lines of resolution setting, determines the length of the time record. Now let's illustrate all this stuff. So here's my time waveform that we saw earlier, and if I use this lines of resolution setting of 400 lines, now this is just a simulation, it's only going to collect enough of the time waveform so that it can produce the spectrum you ask for. It just has 400 lines. Well, the next setting up is 800 lines. It needs twice as much information. For 1600 lines, it needs twice as much again. And for 3200 lines, it needs twice as much again. So none of this affects the samples per second, it just affects how many samples you collect. The more samples you collect, the higher the resolution of the spectrum. But we're not talking about the spectrum, we're talking about the time waveform, and look how much time waveform I collect with 3200 lines. The trouble is that, if I was looking at bearing impacts and so on, the longer the time waveform, there's more revolution, so more impacts and everything else, and you basically have to zoom in to see what you want. And that's all fine. We can zoom in as part of the analysis process, but it's very easy to look at a time waveform and think that you don't need to zoom in. So I kind of like getting my time waveform settings right from the get-go, so that I can just look at my time waveform and say, aha, I can see signs of a problem, or there are no signs of a problem, and we're done. So sometimes though it's good to have all this long time waveform because, and I just mentioned it a moment ago, we can see beating, we can see cavitation, we can see problems in gearboxes that are hard to detect otherwise. Now I hope this isn't too confusing. I'm getting into a bit of detail, but if you look at this closely, the idea of this is a shaft turning, or if it's easier, this is a gear turning. And the vibration analyzer is taking a sample of the vibration from the sensor with a certain time interval based on that Fmax setting. And so even though it's a digitization process, even though it's converting from a voltage that came from the sensor to something digital that we can use inside the software, it corresponds to a time delay which corresponds to the physical thing we're testing, and there's samples taken as the gears are meshing together. I mean, we can only see one gear, but you can see the time between each sample. And you can see then the little red dots represent the actual values that we can use to construct the time waveform. Now this is a bit complicated, and I apologize if you're new to vibration, but I can demonstrate a couple of things with this. So these settings you see here are with the speed of this rotation of 25 Hertz or 25 times per second and an Fmax of 50 Hertz. Now, 500 Hertz. If I increase it, watch what happens. So I'm going to increase the Fmax. And now, if you look closely in there or closely here, we are getting more samples per second. We're getting more samples per tooth mesh. If I increase the Fmax again, we're getting even more samples per tooth mesh, more samples per cycle as the teeth mesh together. Now if I really want to know what's happening as those teeth mesh together, I need a high sample rate. So that's the basic idea here, and I can achieve that either by specifically asking for it, most software will let you do that, or by increasing the Fmax. So now I'm up to 2000 Hertz. But watch what happens as I'm changing this. Watch my waveform. Now this is for a specific resolution. Watch the spectrum down here and watch the waveform as I'll just keep increasing it. There's 2000 Hertz. 4000 Hertz now means I'm getting much more spectrum, and you can see the changes to the time waveform. So as I drop it down to 2000 to 1500 to 1000, so as I reduce the sample rate, this is dictating how many samples I actually get. This is how many seconds there are, or milliseconds, between the samples. If I now change the resolution, I go from 400 lines to 800 lines to 3200 lines, or 16, sorry. I'm getting much better resolution. Like the peaks here are much clearer, but I'm getting more revolutions. So if you're not sure, perhaps go back and play that bit back. Hopefully I said everything that was important there. On to a totally different topic. Does the key phaser notch create unbalance? Well, technically yes, it does. It's a loss of mass at that particular point, so it does create unbalance. But when we balance it, that unbalance is compensated basically. But it is always worth understanding that yes, it does create unbalance, and inserting the key as we're coupling the shafts together also creates unbalance. So you've got to be careful not to balance a rotor and then use a key that causes unbalance. So here is, just in case you're wondering what this question is related to, the key phaser proximity probe is aimed at the key way, or a key, but a key way. And our probes are sitting up near the bearings, but you can see that this will create an unbalance there. Of course, in a machine like this, we've got a great huge long rotor, so the question is what impact does it actually have? But anyway, the balancing process deals with it. Another question: what does it mean if one sees half of a specific frequency in a spectrum? For example, a fan has 14 blades but produces 7x. That's a really good question, and it's probably a bit more advanced. It's not one that I've got a really easy answer 4. So, number one, if you have extreme distortion like the looseness I was talking about, sometimes we get half of that frequency. So in the case of running speed, the looseness which is generated at running speed, we might see peaks at half running speed and sometimes a third running speed. So that's one possibility. Another thing is that if I happen to have a natural frequency at half, now I shouldn't say half x here, it's like, in other words, it's 7x. Even though I've got 14 blades, I can sometimes excite that resonance. It's a long story, but I can excite that resonance. There's also this thing called common factors, when you have interaction between, for example, the fan blades and the diffuser vanes, and same in a pump as well. But we would need common factor of 2. Now this is a complex point, so I've got my simulator here. So what I'm going to do is, so in this case I've got 30 teeth here, there it says 30, and I've got 18 teeth here, so it says 18. Now look, this is really complicated, probably too detailed for this sort of a presentation. But if we had pure prime numbers with these teeth, so what I'm going to do is bump that up to 31, bump that to 19. I'm going to pretend to damage a tooth, so there's our damaged tooth. I'll highlight it to make it easier. And now what happens if that tooth was damaged, it comes into mesh here and it kind of damages that tooth. And then when that tooth, damaged tooth, comes into contact with this gear, it damages that one. Now I'm talking about over lots and lots of rotations. So let's speed that up. Let's speed it up. If we watch for long enough, basically all the teeth end up turning red, and we get even wear. All the teeth share the wear. But if we don't have a prime number of teeth, so I'm going to fix them all, and I'm going to change this to a different combination, just because I know this will sort of come up with the numbers pertinent to the question. I'm going to damage the tooth, and we're already highlighting it. So if I speed that up, a funny thing happens. These teeth do not mesh with every single tooth on this gearbox. So if I speed it up, we see what happens if I go much faster. If we watch for a while, what we will see is that every second tooth gets worn. And so even though I'm referring to gearboxes here, there's a similar mechanism that can happen with the interaction between pump vanes and impeller vanes. It just depends on how many pump vanes and how many impeller vanes there are. But if I slow that down, you can see that every second tooth is damaged. So what that means is that instead of like just getting a peak at 30 times the running speed of this shaft, or 22 times the speed of this shaft, that shaft, which comes out to the same frequency, because they're meshing at a certain rate, we also get a vibration that in this case is half of that frequency, because it's only every second mesh that generates additional vibration. So we can see peaks in the spectrum. In fact, I can simulate it here, and we have this gear assembly phase frequency peak, but like I say, we can see that in other machines as well. Okay, I think it's enough said about that particular topic, but that's a possibility. I hope I'm not forgetting another reason, but anyway. Okay, so here's another question. What is HFD? It stands for high frequency detection. Shock pulse, it stands for shock pulse. Is it an overall value within a high frequency band? Well, sort of. So what happens, and I'll show you some animations in a moment, with certain faults, particularly as bearings cause impacts, so for example a rolling element impacting a damaged area on the outer race or inner race or on the rolling elements themselves, or when gears mesh together and there's sort of like metal to metal contact because there's a damaged tooth, and in other cases. In addition to the vibration that you might expect, we also get these stress waves or shock pulses. That's why it's called shock pulse. Get these shock pulses, and it generates high frequency vibration. It's very low amplitude, so we can't see it in the normal spectrum, but we see it in at very high frequencies, so we can specifically go hunting for it. Now, one way with techniques like HFT and peak view and just normal enveloping, it's sometimes called, or demodulation or peak impacting demodulation, I've heard it called as well. With all those techniques, basically what happens is the vibration analyzer looks at the frequencies above a specific frequency. So in some cases it might just be like when I was getting started in vibration analysis, we used to just take all the vibration above 2.5 kilohertz or 2500 hertz and take all that vibration and go through this process to say, I just want to look at the periodicity of the vibration we see out there. In the case of shock pulse, they have specially designed sensors, let's just call them accelerometers, but they're actually a little different, and they are designed to resonate. So just like you can ring a bell and it'll ring at a certain frequency, these sensors ring at a certain frequency. So whenever there's impacting or lubrication issues, but we'll talk about that separately, whenever there's impacting from the gears or the bearings or other fault conditions, it rings those sensors like a bell, and that software is looking at a little band around that frequency, and it can give it to you as, well, let's call it an overall value because that's what the question said, but it can take it as a value and present that as something that can be compared against alarm limits or trended, or we can actually generate a spectrum and time waveform from that to see, well, how often was the bell rung. So let's just have a look at an animation. First, if we have metal to metal impacting, like the ball landing on the little bar there, the blue wave you see, and this is an animation that I saw from SPM, the blue wave is this stress wave or this shock pulse. The second wave is the bar responding to the impact, which is it resonating. So the resonance part can be detected, but the stress wave or the shock pulse can be detected as well. And you know, in the earlier stages of faults, we may find it really hard to see the resonance, but we'll see the stress wave. So here it is in a bearing instead. So it's all exaggerated. Okay, I'm really trying to exaggerate things, but as the rolling element rolls over the damaged area, you can see a wave rushing out. That's the stress wave or the shock pulse. We can detect that, and then you see the bearing, you know, shake because of the resonance. So we can detect that when the damage is bad enough, and when it is bad enough, which it clearly is here, you can see that periodicity in the spectrum. So as you can see here, there is a set time between each of those impacts, and we will see that in a spectrum, but only when the damage is bad enough that you can see it at the lower frequencies. Okay, how can a lubrication problem be detected using vibration analysis? High frequency techniques that we just talked about, and then you can watch for the bearing failure, because lubrication problems often lead to bearing faults, but the high frequency techniques. Now, one way to do that is with that high F max I mentioned before. I should explain what happens with the lubrication problem. Now, this might be a bit confusing, but imagine you could get smaller and smaller and smaller so that you could go right down where the gears are meshing together and the rolling elements are rolling over the inner race, and we looked at it at a microscopic level, right where those two surfaces are together and they're sort of moving relative to each other. That's where the lubricant actually keeps those surfaces apart. But that you know, and the surfaces are, from a microscopic standpoint, rough. Now, if the lubricant's doing a tip-top job, it's keeping those surfaces apart, and it will generate a bit of noise, and we can listen to that noise with ultrasound. But from a vibration point of view, it just generates, well, just noise. There's no periodicity, so there's no peaks in the spectrum, and the time waveform's kind of boring. But boring is good with vibration analysis. But if the fault gets worse, in other words, we don't have as much lubricant, or there's contaminated with water or something like that, the surfaces start getting closer together, and okay, exaggerated, really close together. Now what happens now is that those rough surfaces are actually impacting each other as it's rolling along, or the teeth are meshing together, But it's still not periodic. It's like bang 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 bang. Just whenever these little mountains and troughs, if you like, collide with each other, we get that bit of vibration. Now this is a basic way of describing it, a little bit exaggerated in what we're seeing, but that creates noise. It excites the shock pulse sensor. We can see it with our high frequency detection techniques, but we don't expect to see peaks appear in the spectrum because there's nothing periodic. We don't expect to see periodic spikes in the time waveform therefore either. Instead, it's kind of like the noise level goes up, and we can see that. It can be detected with shock pulse. It'll tell you if this situation exists. All the techniques can tell you, or you can listen to it with ultrasound and just hear the change in sound and then perhaps look at the time waveform. Okay, changing gears completely. What is your impression about how to quantify the ROI or return on investment in case of implementing this kind of technology? Okay, this is potentially also a big topic to discuss, but I think it's hard to do a very good job of this unless you understand the organization's goals. Like, why is it that the organization doesn't like your machines to fail? Is it because of safety issues or environmental issues? Is it because of the high cost of repair of the machines? Is it because, if failure occurs, you can't provide a dependable service, like if you're a water treatment plant or you're providing water to a city or you're generating electricity? You want to be able to provide that service. If you're in a manufacturing plant, then the uptime is important and the quality of the product's important. You don't want slowdowns, and you don't want those problems. If your company has a lot of standby machines, then a failure of a machine may not result in a loss of production and may not result in a safety incident, but now you've got a machine that's failed, so there are cost implications. So you need to know that first, like what is it we're trying to avoid? And so then you ask yourself, well, what's our current state? Like, are we hitting all of our production targets and we have no downtime, everything? But probably not. So, what is the current state? And what you can therefore answer is, what is the cost of the poor reliability and the poor performance? If your plant, if your rotating machinery just ran and ran and ran and ran and ran and ran, well then your plant would operate at full capacity. Now there are other reasons why you can have slowdowns and other things, but just in terms of the sorts of problems that vibration analysis can help you avoid, there's a good day when there are no problems due to faults that vibration analysis could have detected, and then there's a bad day when you do have a lot of those faults, and you want to compare the two. And so that's what you're aiming for. Now again, we could talk about this for a long time, but vibration can help you detect the problems and avoid all of the consequences of the problems. And what we really want to do is improve reliability so that the vibration analysts don't detect constant bearing faults and unbalanced problems and all the rest of it, and therefore we don't need to have as many spares, which is a high cost. We don't need to have emergency maintenance, which is risky, costly, and everything else. We can avoid a lot of problems if we improve reliability, but we can also avoid fewer, but plenty enough to have a good ROI if we use vibration analysis. And knowing all those things, we can then use criticality analysis to sum up the benefits overall. Now I've got another question on that coming up, so I'll say a bit more about criticality analysis in just a moment. Or how about we do it right now? How do you utilize vibration analysis with equipment criticality? So let's go on from what we were just talking about to say, if we had unlimited resources, you could test every machine with all of the condition monitoring technologies, and you could test them once a week. Hey, you could test them once a day. and therefore you'd know exactly what the condition was. Nothing would catch you by surprise, and therefore you could always plan maintenance well in advance, and life would be wonderful. Anyway, but the reality is you don't have unlimited resources, and so somehow you have to decide, which machines should I test? Can I actually test them all? Do I have the resources to test all my machines as frequently as I really need to? Where can I justify using more than one technology? Oil analysis and vibration analysis and so on. You have to have a way of prioritizing what you do, and equipment criticality analysis helps you to do that. You also need the PF interval to help you make these decisions as well. So let's explain what those things mean. So firstly, from a PF interval point of view, and I apologize if you've seen this before and I probably had it in my presentation, but we're assuming that for a period of time the machine just runs happily and it's doing its job, and something happens which causes it to ultimately fail. So at a certain point, we call that point P in the PF interval, we can actually detect that there's a problem. So now we can detect it. The question is, how long do we have before it functionally fails? So functional failure isn't a catastrophic failure where the bearing seizes and the machine damages itself further. It might be just that the machine's unable to perform its function. We say, well, we got to stop this machine because it can't pump the way it's supposed to, or whatever. But the fact is, there is a time between this point and this point, and knowing that, we can decide, well, if we test measurements frequently enough, we'll detect this. But the truth is that, number one, that curve is a little different to what is often depicted. The condition doesn't degrade very much for a while, and we can detect it, but the actual health of the machine hasn't degraded much. But it's not until it really starts to fail, and that's really in the sort of the last hours and days of the failure, when the bearing starts to make a sound that you can hear, or it gets hot, or it becomes loose because of the loss of material. So it's really in the sort of the last stages. So that's one point I want to make. And the other point I want to make is that there is varying times. It all depends on the load and the speed of the machine and the failure mode, like what's causing it to fail. We could have years of warning. We could have seconds of warning. So that's why big critical, there's that word, critical machines that can fail catastrophically, like big steam gas turbines and boiler feed pumps and so on. That's why they're monitored with protection systems, that when they see certain situations arise, boom, they shut them down carefully so there is no safety incident. But I still haven't mentioned what criticality is, so let's do that. On a really simple basis, we can just say, well, how critical is a piece of equipment? Is it moderately critical? Is there a major consequence of failure? Is there an extreme consequence of failure? And unfortunately, most people kind of think of equipment in just this way, or maybe even simpler than that. It's critical, or it's essential, or it's non-essential. It's just as simple as that. And so if you look at a production line, you might say, well, if any one of those machines fails, and then the production line stops, so therefore they are all equally critical. Well, no, that's not the case. So what I'm going to do is I just need to jump ahead, or we'll be here forever. The number one thing I'm going to do is say, well, what do you mean by the consequence of failure? Well, all of these little statements here are saying, well, the consequence of failure gets worse as I go from left to right. So this gets a score of 1, this gets a score of 5. This is sort of the worst thing we can think of. But just from an equipment failure point of view, what about people? The minor first aid or no first aid, single or multiple fatality. What about from the environmental point of view? This is really bad. What about from a production point of view? No impact on production versus it's going to cost us more than $10 million of loss if we lose this machine. What about from a customer quality and the impact on the customer point of view? Here our food product that we're producing kills our customers. That's pretty bad. So I could go into a lot of detail here, but what we need to do is sort of say, well, for each piece of equipment, what is the consequence of failure? And it's going to vary in each of these categories. And secondly, we have to say, well, how likely is it that it is going to occur? Because you may have a whole lot of machines in a row that you think, well, they can all stop production, but are they all capable of poisoning the customer? Are they all as costly to repair? Do you have the same sort of spares for each one? Are they all as reliable as each other? You may have one machine that's been running for the last 15 years and doing a great job, and another machine that fails more frequently. I need to pay more attention to that one that fails more frequently. It becomes more critical. Criticality is the combination of the consequences of failure and the likelihood of failure. But we need to go a step further, because not just the likelihood of failure being initiated, it's the detectability. Because I might have a machine that fails quite frequently, but I'm 100% sure I'm going to detect that it's occurring, so it never gets to fail. And so, yes, we can be worried about these things, but I'm so sure that my protection system will function that the detectability is very high. Therefore, it actually reduces the criticality of the equipment. Now, without that protection system, we would have had a highly critical piece of equipment, and that's what justified the detectability. And that's what goes back to that ROI question recently. Here I am, it's already 50 minutes, I apologize, but anyway, hopefully it's useful. So we justified the expense of the protection system because we needed the detectability to be very high. Anyway, I could talk about this for a lot, but this really helps you justify programs, both from a cost point of view and to decide which machines need to be tested. We need a combination of detectability, reliability, and consequence of failure, which all creates the criticality ranking. Okay, on a different topic, how the trends could be used to analyze the data. Something I didn't mention in my webinar actually, and I should have, because whereas we measure the vibration, we can look at just the overall level, and we can look at the spectrum and time waveform and phase and orbits and things that I did mention. With the overall level, and with chunks of data extracted from the spectra that we've been collecting, we can see how machines changing over time. Because to a very high degree, if the vibration isn't changing, then we sort of become less worried about it. Even if the amplitude's a bit high, we can say, well, it's not changing. Now, it doesn't mean we don't need to consider whether that's a safe way to operate the equipment, and we might be inducing failure. But in terms of priorities, you need to deal with the machines where the vibration is changing before you deal with the machines where the vibration isn't changing, assuming that the criticality is the same. So we always need to remember criticality. We need to deal with our critical machines because the risks are much higher. So with our trends, we can see how quickly the problem is developing. We can see the trend going up quickly means that the condition is degrading. But we can also extract frequency from bands in the spectrum. We can take the vibration just around that 1x peak that I talked about almost an hour ago. If we see that changing, we can say, well, the unbalance is getting worse. Now, there is a special spectrum plot called a waterfall plot, and we can see how different peaks are changing in amplitude over time. But a trend, which sort of extracts its information from all those spectra, gives us very good information. And it's also very good to extract that machine condition information that I just talked about and compare it with other parameters. And they could be temperatures, flows, production rates, other parameters, and we can say, well, let's see how the vibration's changing, against these other parameters. We might notice that the flow is changing and the vibration is changing. Now, it could be the flow that's affecting the vibration or the vibration that's affecting the flow. You'd have to figure that out. But it is a very good thing to do, to look at trends of both those values. And it really helps us to understand the history of the equipment health. We can look back if you've been running your program for 5 years, look back over those times and you can see, here's the time when that bearing failed. Here's the time when the unbalance suddenly got worse. Here's the time, we can kind of see over a period of time and learn from that. Okay, hopefully that answers that question. If a random frequency or a peak at a random kind of frequency shows up without harmonics, will that be a concern? The first question you always have to ask is, did it do that and there was a high amplitude peak or a low amplitude peak? Generally speaking, when low amplitude peaks pop up, you sort of say, well, I don't care so much. Now that all depends too, because the peak that popped up might be related to a bearing frequency, and hopefully we would have seen signs of that before it popped up in just your normal spectrum. But a few things to think about, and you can decide whether it's bad or not. Number one, could it have come from an external machine? Maybe the plant's operating differently now, or for a variety of reasons now the vibration from an external machine can be transmitted through to the machine you're testing, and that's actually the source of the vibration. So you may want to investigate why it's changed. Why am I seeing it now and not before? Might be a problem with that machine, but that's one way to explain it. In a rare case, you will see a peak at, for example, the ball pass outer race frequency, because and that's the frequency that we normally see when there's damage on the outer race, but damage on the outer race will create harmonics as well. But if the outer race was out of round, we can see a peak at this BPFO without all the harmonics necessarily. Anyway, when you see any peaks, you then got to sort of put your mind into a certain state. We're going to look at, is it synchronous? That wouldn't be a random frequency, I suppose, because that would, synchronous means 1x or 2x or 3x or 4x or 5x, 6x, an integer or a whole number multiple of running speed. So if I suddenly saw a peak come up, I'd have to think, what would generate vibration at exactly 5 times running speed? Maybe it's actually a forcing frequency. Maybe it's the pump vane rate that I've never noticed before and it's suddenly growing. Or it's usually something like that. If it's subsynchronous, which means less than 1x, I have to think differently. Belt wear will show up as a peak there, but sometimes you get harmonics in that case. Turbulence will show up, although it's usually a nasty big blobby peak. That's a technical term, blobby peak. But so we might see that. Anyway, we need to think about that. And the non-synchronous, could be an external machine generating the vibration. Might be from the bearing as I described. It could be from another part of the same machine. If you've got a gearbox or belt, then a peak at non-synchronous could be a synchronous peak from the fan, not from the motor or something like that. And then, look, in a rare case you'll have something called intermodulation, which is like a sum or a difference frequency. So let's say we have a peak at frequency A due to something in the machine and a peak at frequency B due to something else in the machine. Sometimes we'll see a peak appear at a frequency equal to A plus B, and sometimes A minus B or B minus A, whichever brings a positive frequency. And so we can look at it and say, what does that mean? Is this new peak that showed up, what does it mean? Well, you don't have to become too alarmed. You might ask the question, well, why am I seeing it now? Like, what mechanically has changed so that these are interacting with each other? Anyway, enough said on that, I think. If I see a peak of vane pass or blade pass frequency, what would be the defect? There are a few possibilities. Uneven clearance between the vanes and the volute, or the sort of between the blades and the housing and so on, can cause that. If the blades or vanes are bent or damaged in some way, or the guide vanes are bent or damaged, we expect the water or the air or whatever it is to sort of flow through the pump, but as those blades turn or as the vanes turn, this should be in terms of a once per revolution point of view, it should be sort of even, if I can put it that way. That's the way it should be designed. But with damages to the guide vanes, for example, or the blades themselves, or if there was misalignment or something causing change in those clearances, then we can see an increase in amplitude at the peak. It's common to see a peak, but an increase in amplitude is what we're worried about there. And since we're talking about pumps, what is the vibration analysis device? Well, I would argue that you want a two-channel analyzer, two-channel vibration spectrum analyzer, portable data collector, measurement device, whatever you want to call it. Two channels is good because it allows us to measure phase much easier. But we definitely want spectrum and time waveforms from that pump, and we want high frequency detection, just like we talked about quite a while ago. We need to be able to do those things. So now, which actual commercial product? I couldn't tell you that. We work with everyone. Everyone has a great product. But what we're going to do on our pump is we're going to use our vibration analyzer. We're going to put the sensor on there. We're going to get a little spectrum from it, and I'm going to measure maybe in the horizontal direction as well. I'm going to measure over on the pump, and I'll detect all sorts of things. Could a poor alignment technique be the cause of bearing looseness? Now, I had to think about this and think, could you align a machine so badly that somehow you made the bearing loose? But what can happen is misalignment can damage the bearing. So with misalignment, you're putting a lot of extra load on that bearing, which will cause it to fail. It's inevitable. It will fail prematurely. In other words, earlier than it really should have. And so with that wear or loss of metal, or whatever you want to call the damage that occurs, we can increase clearances within the bearing, and we may diagnose that as looseness, but that's a real late stage bearing fault. I think that's a fair enough answer to that. If familiarity with the equipment is very important, do you recommend in-house vibration programs over contracting the service? So first I should comment on the basis of the question, and I absolutely positively believe that it's helpful to understand the machine and its failure modes. If it's just this big metal box and you sort of wonder what's inside there, it's much harder to do vibration analysis. Much harder. If you know what's inside, then you can say, well, okay, I can imagine now if I'm seeing those harmonics that we talked about earlier, or a peak at 6x, or whatever it is we're seeing, you can sort of think about what's inside the machine, or if we see an increase at the pump impeller rate, the pump vane rate or blade pass rate, you can think about what's inside and make a better judgment. And that's why it can be that a person who was a mechanic on those machines and repairing those machines can do very well at vibration analysis, because they at least understand what's going on inside. So then the question is, well, if you're providing that as a service, can you still do a good job? Well, the answer is yes. I mean, sometimes the consultants may be more familiar with the machines at your plant because they've seen those machines at other plants, more familiar perhaps with people at the site. There can be vibration analysts who never take the time to really understand what's inside the machine. So that's one question, but either way, who's ever doing a vibration analysis, you should take the time to learn about the machines and ask all the questions that they can. There are pros and cons to in-house over, service providers. Service providers might have all the gear and experience and training and certification, and you can get started more quickly. If it's an in-house program, they probably have a much better relationship with the maintenance people and production people. They can respond very quickly if there's if someone hears something, or there's a process parameter that changes, or for some reason people suspect a fault condition. It's easy to do follow-up special tests. There's pros and cons. Okay. What is your experience with algorithm software diagnosing vibration readings, and if you feel these will phase out certified analysts? Actually, I seem to remember this during the webcam. Look, the bottom line is, it appears to be inevitable that one day computers and the robots, probably not robots, probably just computers, will be able to measure vibration and detect fault conditions. Now, it takes a lot of experience with machines to be able to diagnose faults, because you really, one way or another, you have to know how the vibration changes, and you do that either by seeing enough faults that the software kind of learns how the vibration changed that led up to the fault condition, or analysts have to sort of say, well, you need these features from the data and you need to interpret them in a certain way. But I can tell you that actually way back in the 90s, I was involved with a program like this, and we actually developed a pretty darn good system. It was a pretty good system. And we weren't trying to phase out vibration analysts. The way we looked at it, and the way I'd still look at it today, is that these techniques can help the vibration analyst. Because if you're out there measuring lots and lots of machines, and then you've got to sit there and analyze lots of data, because so few people have really effective alarm limits set up, that's a lot of work, and it's really easy to make mistakes and miss faults because you're just churning through so much data. So an automated diagnostic system that can look at all that data and say, oh, hey, I see a problem here, and there, that focuses your attention. And now you can analyze that data first, knowing what the computer said, but you're using your expertise to really get to the bottom of it, and then you understand the process and the production demands and all those other things, and you can help make the decision about what to do. You can go and perform special tests. So I would just say that how can I put this? If your primary role is to test the machines, and from an analysis point of view you're really focusing on rolling mat bearing faults, then yes, the computers might one day, with online systems, with wireless sensors and all these things, everything has to be justified. Everything has to have an ROI. But it could be that one day, a lot more machines are being tested remotely. But that's a long way off. And then of course software can then take that data either from the portable system or from these online systems and do some analysis. So basically you need to learn how you can add more value by diagnosing a wider range of faults, by being able to do special tests that enable you to diagnose a wider range of faults. Anyway, I think it's enough on that topic. What is your sense on trending condition-based maintenance data, condition monitoring data, and aligning that information with real-time process data that may include process hiccups, like spikes to temperature variations in process flow, etc.? It makes perfect sense. It's a very good idea. It definitely helps. So I think I mentioned a little bit about that in the trending question, but vibration analysts should be, let's say condition monitoring specialists should be looking at the entire health of the machine, and the performance of that machine tells you about the health. It tells you whether some mechanical fault is affecting the performance, or the performance is affecting the mechanical health, or a bit of both. And the performance includes just the way it's being operated. So it is very useful information, and for sure, if we have an online monitoring system, or even if we haven't, if we can look back and say, aha, this vibration change we observe, it happened at the same time that some other process parameter changed, and then we can investigate the reason. Well, why did it change that way? It really is good information to have. During the presentation you said that the measurement has to be taken at the same conditions, but what about different process conditions between measurements? Are those measurements useless? No, definitely not useless. It just poses a bit more of a challenge. The best thing for a vibration analyst is where the condition of the machine just does not change from test to test to test, and so when you see a change in the vibration, you say, well, the only explanation is that the condition is changing, and now you have to interpret what that change means. But if the process conditions change and you see a change in the vibration, you're then saying, well, gee, why is it so? Was it the machine health, mechanical health that caused the change or the conditions. Now look, when you dive into vibration analysis more deeply, there's an awful lot you can learn even with varying conditions. Number one, on the one hand, if you've got bearing faults, for example, you always see harmonics at non-synchronous ratios of running speed, like 3.09 and 6.16 and these sorts of frequencies. So regardless of the machine running speed, you will see these peaks. They are multiples of running speed, and that's why I talked about orders way back at the beginning, 1x, 2x, 3x. If you know what the running speed is, even if it changes, you can still figure all this stuff out. So there are certain patterns that only show up in certain situations, and we can use that information. But otherwise, what can happen if just generally the amplitude changes, gets a bit trickier because of resonance. Now, resonance amplifies vibration just within a limited band. So if under one set of conditions the speed is such that resonances are not excited, then all the amplitudes of all the peaks you could kind of argue are related purely to the condition of those individual components, the pump impeller, the gears, the bearings, and so on. But if the machine speed changes, now the vibration may coincide or be just close to a natural frequency, therefore resonance occurs, therefore the amplitude changes. And people can easily jump to a conclusion and say, goodness me, look, the 2x peak is really high, we better align this machine. But it's only that the 2x happens to be closer to resonance now, and it increases in amplitude. It's got nothing to do with the underlying state of misalignment, it has everything to do with the resonance. So you need to sort of get a sense for how the condition of your machine and how the vibration will change under different conditions. Because even if the speed doesn't change, just sort of loading can really affect everything from the magnetic fields inside the motor and the amount of slip to what's happening as the liquid, for example, goes through the pump and so on. That's why it helps to really understand your machines and not just look for patterns and jump to a conclusion. Oh, there's that terrific question again. What, the same question again? What is the best way to be trained? Yes, you are right. See, this training works. Now you know that Mobius Institute's the best way to be trained, because we have all those training centres, so there's one close to you. You can learn online or offline. You can use all those animations. I mean, let's face it, all the things we've just talked about, weren't they easier to understand with all those animations and simulations? You bet they were, and we use them all the way through our classes, and no other training company has anything like it. Not a shadow on what we have. We have literally hundreds of animations, and gee, what are we up to from simulators? Gosh, there must be 300, 400 related to vibration, something like that. Not that we use every single one in every single class or anything like that, but anyway, yep. And accredited certification. There is no higher standard to our certification. And what's the next question? The conferences. Yes, come to a conference, speak at the conference, share your experience. It's fantastic, but you can't just rely on that 1, 3 or 4 or 5 day training class to be an expert in vibration. And yes, there are situations like the one you're experiencing right now where you can continue to learn, and that's fantastic. But we run those conferences so that you've got lots of opportunities to learn. Learn from the other attendees, learn through workshops, learn through fantastic case studies, really interactive case studies. It's a great way to learn, and if you're up for it, share your knowledge. Okay, that's all the questions. There were a couple of questions I left out just because of the nature of them. I thought we could be here for a very long time trying to answer them, and I thought they were a little bit left of center. So if you have more questions, feel free to email them through. But look, I really thank you for listening to this whole video, if that's what you did. I thank you for listening to the webinar. I hope it has helped you. And the next time you think about training or a conference, now you know where to go. Thank you very much. Oh, and there's our website. We can always learn much more. Bye now.